So, of course, this term is smaller than the magnitude of fxx plus fyy, right? Because you're taking, this quantity and you're subtracting something from it. If we didn't have the d at all, then this would be the magnitude of fx plus fyy, right? So we're taking something and we're reducing the magnitude of it by subtracting this positive term. And if that's smaller than this, what can you tell me about the sum of a number and a number with smaller magnitude than the number? Can this minus get you back to negative? It can't, right? So like, basically, if this is positive, then I am adding something that's the same size to it. It stays positive, right? If I'm subtracting, I'm still positive because I'm subtracting a number that has smaller magnitude than that. On the other hand, if fxx plus fyy is negative, we're either adding a number which has smaller magnitude than fxx plus fyy, or we're subtracting a number, right, that's smaller in magnitude than f. So long story short, this means that lambda plus and lambda minus, they're both positive, or lambda plus and lambda minus, they're both negative, right? So if that's the case, right, and we just argued that it is, we also have to have the case that, if you think about it, it's enough to just check xx, the derivative itself, right? Because if the if the xx derivative is positive and the xy derivative is negative, I always get stuck on this particular part of the proof, but you can argue that the xx derivative governs the sign of fxx plus fyy, all right? So that's why I say in the notes, I say if d is positive, then, oh yeah. I need to think about what d positive means. That's what tells it. D positive means what? fxx fyy is greater than fxy squared, right? What does that tell you? Could you have the xx derivative positive and the yy derivative negative in this case? No, so you see that these must have the same sign if fxy is non-zero, right? Now, if fxy is 0, then we could give a different argument, I think. But anyway, you see that the sign of fxx and fyy is shared. Therefore, we can check on whether we're getting the case that they're both roots are positive, right? If both roots are positive, which is coming from the xx plus the yy derivative being positive, that has to happen in the case that both of these derivatives are positive, all right? And in that course, this gives you a local what? Min, right? Local max in the other case. So the minimum is going to come from when fxx is positive, and the maximum is going to come from when fxx is negative. Again, their fate is shared because the product of their derivatives has to be positive, and as such, well, I guess I could say that this is okay. Let me not be an idiot. This is greater than or equal to 0, right? It has to be non-negative, and certainly if the product of the derivatives is non-negative, we cannot have one positive and one negative, right? I hope that's convincing. And so you put this all together, and you have the theorem, right? You might notice the theorem over here. So what I'm really telling you is that this choice of checking the second partial derivative with respect to x is completely arbitrary. We could just as well have written check fyy at the point is positive, and fyy at the point is negative. Dr. Schmidt has thought about this a lot. And when he presents this material, he looks at it in terms of kind of a second directional derivative. He argues that it's basically, if you look at the second directional derivative, whatever that means, you want there to be a positive second directional derivative in all possible directions to have a local min, and you want to have a negative second directional derivative in all possible directions to have a max. But what is xx and what is fxx? It's essentially a second directional derivative in the x direction, right? And likewise for the y one. And so I guess really what Dr. Schmidt is saying is that not only can you replace it with xx or yy, you could replace it with any possible second directional derivative, whatever that is. You have to ask him. He's the one who defined it. So, but anyway. So that's the second derivative test. Why is there no first derivative test? I mean, first derivative test played a pretty big role in Calc 1, you remember? Why is that gone now? It's what?
I said that's a good question.
It's a good question. I mean, it sort of isn't. Like the analysis we were doing at the start of class was kind of a first derivative test, wasn't it? Because what we were doing is the thing is so the first derivative test basically is based on the idea, if you think about a critical point in one dimension, you can either approach from what? The left or the right, right? So as long as you're going up on one side and you're going down on the other, that means you're a what? You're at either a max or a min, right? So you're either going up and then down, that's a max. If you're going down and then up, it's a min, right? But if you're just going up, it's neither a max or a min. Or if you're just going down, it's neither a max or a min, right? The thing that plays the analog of that currently is when we thought about those case-wise discussions, right? Like thinking about going close to the point from one direction versus another, getting values that are getting positive on one side, negative on the other side. Like that's the kind of analog of the first derivative test. But it's not it doesn't have the role of a proper theorem. Like I don't have a first derivative test theorem to tell you. All right. So how about, yes?
What does saddle point look like graphically?
Like a saddle. So, I mean, sorry to be boring, but like this. Something like that. So it's going up one way. I'm trying to think. I can never draw a saddle point worth anything, but I think, I'm trying to think, this one, I'm pretty sure z equals to xy does this. Z equals xy, it can't be quite this, can it? Because z equals xy is 0, if you think about that graphically, right? Let's think about this for a bit. So I'll draw the graph in red, I guess. Z equals xy is 0 if x is equal to 0 or if y is equal to 0, right? What are those? Yeah, the axis, right? So we've got basically, here's part of the graph, right? And all right, how about z? All right, so some other things we could think about. Y equals to x, right? Z is equal to what? X times x, x squared, right? Y equals to minus x, though. That gives us z is equal to negative x squared, right? And so, all right, so if this is x and this is y, then if we think about x equal to y, it's going up, right? So it's kind of like going up here and also here. But if we look at y equals minus x, like over here, we're going down. We're going down. Again, I can never draw this thing worth anything. Maybe it helps to just look at it this way. Y x, right? So here's level 0. You know, if I think about f of x comma y equals to xy as my function. So like my contour, here's, you know, c equals to 0 here, right? But if I have xy equals to 1, that's y equals to 1 over x, right? So that looks like here and here. These are my, you know, this is xy equals to 1 solutions, right? If I look at xy equal to minus 1, then it's just the same, but over here, right? So what I'm trying to graph, I can't ever do it in 3 dimensions worth anything, but in back here and up here, it's going up like that. But in these 2 quadrants, it's going down, as you can kind of see, like there's minus 1. And as you go further out, like xy equal to minus 2, it's further out here. Xy equal to 2, it's further out that way. So it's going down like that, and it's going up like this, right? Yeah, that's a saddle. Now, we still use the word saddle point for a function of 3 variables, even though I can't draw that there. But what it would mean is that if you look at all possible level surfaces close to the vertical point, you'd find some level surfaces which have a negative value and others which have a positive value. Anyway, I have a half a dozen examples of this theorem to show you guys, but obviously we're out of time for today, so I'll stop here.